This is the second lecture on the CTFT. In this lecture, we will continue by practicing some examples on how to compute the CTFT of different signals. Let's start with a simple example where xt of t is equal to delta t, which is the impulse function. So it's the impulse at t equal to 0. Now by applying, so this is t and this is x of t. Now by applying the formula of the CTFT, we know that the CTFT xj omega of the delta is equal to the integral between minus infinity and plus infinity of delta t e minus j omega t dt, which picks up the value of e minus j omega t at t equal to 0. So this is equal to e minus j omega 0. Again, this follows from the property of the impulse function, which is equal to 1. So notice here that x of ej omega is a constant function. So if you want to draw it here, so this is omega, and this is x of j omega. Again, here because it's real, so I don't need to draw the amplitude and the phase. Or this is exactly, the amplitude is equal to the function itself. So here, let's say this is 0, and this would be x of j omega. So it's equal to 1 everywhere, which means that the impulse function has all frequencies, and sometimes this is referred to as the if this corresponds to a noise, this is referred to as a white noise because it contains all the frequencies. In the second example today, let's try to apply the formula of the inverse Fourier transform. So the question here is about, we are given the h of g omega, which is the CTFT of a low pass filter. So you can see the figure of it here. You can see that this is a low-pass filter because it lets the frequency between minus b and plus b pass through the system with a gain equal to 1, so there's no gain, but it kills everything that is outside here. So think of it as multiplying your frequency signal by this filter. And we'll get back to this because when you input a signal through a system, it's gonna be, the output is gonna be a convolution, but it's a multiplication in the frequency domain. So the spectrum of your signal is gonna be multiplied by h of g omega, and this is why it lets only the frequencies between minus b and plus b pass through. Again, I'll come back to this later, but here let's think of it as just as a simple application of the inverse Fourier transform. So we are given the following h of g omega, which is equal to 1 if omega is between minus b and plus b and is equal to 0 otherwise. And the question is to find the impulse response h of t of this low pass filter. Again, to find h of t, we need to apply the inverse Fourier transform. So h of t is equal to 1 over 2 pi the integral between minus infinity and plus infinity h of g omega ej omega t dt. But here it's easy because I know that this is equal 1 over 2 pi. The integral is gonna be between minus b and plus b, 1 ej omega t dt, and this is gonna be equal 1 over 2 pi. And I am actually here I made a mistake, so here ej omega t it should be d omega here. So this is going to be equal, so the integral of ej omega t d omega, so this is going to be ej omega t divided by jt between minus b and plus b. So this is going to be equal to, you can take the j outside, so it's going to be 1 over 2 pi j e j bt minus e minus j bt. Well, here you can take the t is constant here, so this is omega equal to minus b and omega equal to plus b. And this is, you can bring the j here and the 2 here, and this is sine, so this is going to be equal sine bt divided by pi t, which is the sinc function. So this tells you what the impulse response of a low-pass filter looks like in the time domain. So I'm gonna go through it in more details in a little bit. So this slide summarizes the result from before. This is the CTFT of a low-pass filter that lets only frequencies less than b, the bandwidth limit, go through. And the impulse response h of t is sine of bt divided by pi t, and this is the sinc function, and it looks something like this if you plot it. It's very important to understand this and keep this result in mind because it's going to be very useful. Let's do one more example here, and let's look at the following question. So we're given a signal x of t that looks like it says a box function here, which is 0 outside the interval minus t1 plus t1, and it is equal to 1 inside this interval. So I think of it as a dual of the previous problem because the signal in the time domain looks like a box function, and the question is to find its CTFT. Now again, it's the same trick again. What we have to do is just apply the formula, and we get that x of j omega is the integral of the signal, which is 1 here. So the signal is 1 times e minus j omega, and you should pay attention here that we change the boundaries of the integral to correspond to where the signal is non-zero, and then the rest is just application of the integral of an exponential. And what you get that the signal is 2 sine omega t1 divided by omega. So it's kind of look also like a sinc function, but there's no pi here, and there's an extra 2 here. So this points to some kind of duality between time and the frequency domain, and we'll talk a little bit about this also towards the end of this chapter. So in some sense, a box in the time domain will be a sine omega t1 divided by omega in the frequency domain, and the other way around. The box in the frequency domain, which is a low-pass filter, is a sinc function in the time domain. In the next few examples, I'm going to focus on computing the CTFT of periodic signals. The first example is the CTFT of a complex exponential, and the question here is to find the CTFT of x of t equal to e j omega 0 t, and to prove that is actually equal to 2 pi delta omega minus omega 0. Here it's easier to double check that the result is true by using the formula of the inverse CTFT. So we check that the inverse CTFT of 2 pi delta of omega minus omega 0 is actually x of t, which is 1 over 2 pi, the integral of 2 pi delta minus delta 0, delta omega minus omega 0, ej omega t d omega. And this part, 2 pi is going to cancel 2 pi here, and this integral is going to be equal to ej omega 0 t, and which gives us the result here. Now what is this saying is that the CTFT of ej omega 0 t is equal to an impulse in the frequency domain at omega equal to omega 0. So this signal has a single frequency, single tone at omega equal to omega 0. That's what you should keep in mind. So this is an important result. And this is going to allow us to find the CTFT of cosine and sine. So the CTFT of cosine omega 0 t, by using Euler's formula, we get that the cosine of omega 0 t is equal to pi delta omega minus omega 0 plus pi delta omega plus omega 0. So the cosine omega 0 t has two impulses in the frequency domain, one at omega 0 and one at minus omega 0. And it makes sense because cosine is a single tone at omega equal to omega 0. Now, we can also apply the same principle to get the CTFT of a sine signal, sine omega 0 t. Intuitively, it should contain an impulse at omega equal to omega 0 because this is corresponding to the period or the frequency. And we get this by doing the CTFT. So we have a pulse at omega 0 and a pulse at minus omega 0, and both of them has amplitude pi over j. Actually, here there is a typo, so this should be here. This should be a minus sign, and this is minus. I'm gonna end this lecture by giving you a few examples to try yourself at home, and I'm giving you the answer here so you can double check your results. So the first problem is to consider the following signal x of t given here in this figure, and it's also given by this expression, and to prove that its CTFT has the following expression. And another example to do at home is the following x of t, which is equal to 1 between 0 and 4, and to prove that its CTFT has the following expression. So maybe here I did not specify it, but here it's equal to 1.